Hello there. Welcome to Just About Space. Tonight we'll drift into one of the most unsettling and strangely beautiful ideas in modern physics. The possibility that gravity, that ancient and invisible force that holds our universe together, might not be real at all. At least, not in the way we've been taught to understand it. You know gravity. You feel it every second. It tugs at your arms, keeps your feet planted, tells your body which way is down. It binds planets into orbit, sculpts the dance of galaxies, shapes the very curvature of space-time. It's one of the first forces you learn about as a child. An apple falling, a swing slowing, your body growing heavy with sleep. But what if that feeling is an illusion? Not a trick or a hoax, but a side effect, a consequence. A surface-level experience of something far deeper and stranger. There are theories, serious ones, that suggest gravity doesn't exist as a standalone force at all, that it emerges from entropy, information, or the holographic nature of the universe. Tonight, we're going to let go of what we think we know. You don't have to solve equations. You don't even have to believe anything. Just float with me through a space of curious minds, soft ideas, and the gentle possibility that everything we take for granted, weight, mass, force, is something far more slippery than it seems. Now, lean back, and imagine a universe where gravity never existed in the first place. Let's begin with a question that's as heavy as it is light. To explore this, let's sit still for a moment. Feel your weight in the chair or bed, that familiar downward tug, the ache in your muscles after a long day, the softness of your mattress resisting your fall. Gravity is always there. We don't question it. Isaac Newton in the 17th century was the first to codify gravity as a universal force. Apples fell. The moon orbited. The equations worked. He imagined gravity as a pull, an invisible thread stretching across space, binding masses together. Elegant, simple, useful, but Newton himself never claimed to know what caused gravity, only how it behaved. He left the question dangling like an apple on the branch. Then came Einstein, centuries later, and changed everything. In his general theory of relativity, gravity stopped being a force. Instead, it became geometry, the bending of space and time by mass. Earth doesn't pull you, it warps the fabric of space-time, and you roll downhill in that curve, like a bowling ball resting on a trampoline. Mass sinks the fabric and everything nearby slides toward the dent. Even light. Gravity became distortion. Gravity became illusion, of a kind. But what if even Einstein's revolution didn't go far enough? Some physicists today are whispering an even more radical idea that gravity doesn't exist on its own at all, that it might emerge from deeper quantum processes from entanglement, information, and thermodynamics. What does that mean? In short, it means gravity might be the result of information trying to balance itself. Verlinde argues that space itself might be woven from tiny bits of information, microscopic building blocks like pixels on a screen. When you move mass like you or a planet through that information, it causes a change in entropy. And like all things in the universe, systems try to return to balance, that push back toward balance. We experience it as gravity. In this view, gravity isn't a real force. It's a side effect, a statistical illusion, a thermodynamic bookkeeping entry, as if the universe, when rearranged by matter, whispers, no, let's tidy this up a bit, and in the process tugs things together. This is not science fiction. It's not some fringe idea scrawled on a napkin. It's serious physics, still unproven, still controversial, but deeply considered. And if it's true, it would turn our understanding of reality inside out. If gravity is an illusion, an emergent phenomenon, then what else might be? Mass, inertia, space itself? It also raises uncomfortable questions. If gravity is information, then who or what processes it? Are we living in a computational universe, where all matter is merely a complex tangle of data? These aren't just thought experiments. They're active fields of research. The Event Horizon Telescope, which captured the first image of a black hole's shadow, is one small piece of this enormous puzzle. The James Webb Space Telescope peers into the deep past, watching galaxies swirl and collide in a cosmic dance dictated by what, exactly? Is it a force? Or is it memory, entropy, and probability stitched together to form the thing we call gravity? We might not know the answer in our lifetimes, but here's the wonder. Even without the answer, the question shapes us. Because if gravity is an illusion, then so is the boundary between what we think we know and what remains beautifully, endlessly unknowable. You don't fall to the earth. You follow a line written into the curvature of something you cannot see. Maybe that's the universe remembering where things belong. And maybe, just maybe, the truth is stranger than even our wildest definitions. Let sex keep falling, only this time, through theory itself. If gravity is not a force, but a side effect, then we must ask, what is it an effect of? Let's begin here. Not with the falling apple, but with the empty air between it and the ground. Because if gravity is an illusion, it's an illusion cast by the very fabric it distorts space-time. We often imagine space as empty, a void, a vacuum, a silent backdrop, but space is not nothing. Space has structure, texture, rules. It stretches, it bends, it can ripple, like the surface of a pond. And those ripples, known as gravitational waves, are not theoretical anymore. We've detected them. We've felt the aftershock of black holes colliding in galaxies too far to name. Which means space itself is not passive. It reacts, it moves, it has memory. Einstein taught us that mass bends spacetime, and spacetime tells mass how to move. But that elegant sentence conceals something profound. Space is not fixed, it is a participant in the game. Now imagine this. You're floating in deep space, away from any star or planet. You feel nothing. No pull, no push, no motion. But what if that nothing is an illusion too? What if the fabric beneath you is constantly recalculating, adjusting for the presence of particles, the flow of time, the distribution of information? This is the beginning of a radical idea that space-time itself may not be fundamental. What if space-time is built on something deeper? Not strings, not atoms, not quantum fields, but information. The idea isn't new. In fact, it's gaining traction in the deepest corners of theoretical physics. Think of the holographic principle, a concept born from black hole physics. It suggests that the information describing everything inside a volume of space, say a room or a planet, can be fully encoded on its surface like a 2D hologram that creates a 3D illusion. It's set as if the universe is projecting itself. This leads to an even stranger implication. Maybe space, time, and gravity aren't the screen, but the illusion on the screen. The real code of the universe might live in quantum entanglements, the invisible threads of probability and correlation that bind particles across distance. Eric Verlinde's entropic gravity theory takes this idea a step further. He proposes that gravity is a result of microscopic information shifts. When you move a mass, you alter the information content of the universe around it. And like a spring returning to rest, the universe responds not with a push or pull, but with an entropic tendency to restore balance. It's Sut's, not force. It's Sut's preference. The universe prefers high entropy. It prefers to be messy, but predictably so. Let us bring this home with a thought experiment. Imagine a rubber sheet stretched tight and a heavy ball placed in the center. Now place a marble near the edge. It rolls inward, not because the ball pulled it, but because the surface changed. That's Einstein's gravity. Now zoom in, way in beneath the rubber, to the threads that make it up. What if those threads aren't rubber at all, but tiny lines of code reacting to mass and motion, reshaping the surface automatically, silently, instantly. That's SIP's entropic gravity. In this view, when you fall, it's not because something yanks you downward. It's because the underlying code recalculates, rebalances, and in doing so guides your trajectory. It means every orbit is a compromise. Every step is a statistical dance. Every sunrise is the result of something deeper than force, something written into the very tendency of the universe to organize itself. But here's where it gets even stranger. If gravity is emergent from information, then what is mass? Some physicists now wonder if mass is simply another illusion, a resistance to acceleration born from the network of entanglements a particle holds with the rest of the cosmos. You move it, and the universe must update its information everywhere. That costs energy, that feels like inertia, that looks like mass. In this model, the universe isn't a machine, it's a process. A living, breathing, recalculating tapestry of information. And you, your body, your atoms, your brain are entangled within it. You are part of the equation. You are not falling through space. You are flowing with the update. Your path, your pull, your stillness, all dictated by a structure you'll never see, but one that has shaped every step you've ever taken. So next time you drop something, a pen, a cup, a thought, wonder not at the pull, but at the pattern, because beneath space is shape, and beneath shape is entropy, and beneath entropy is the whisper of something we haven't named yet. Something that doesn't pull. Something that remembers. Let Tets keep going. It sets elegant. It sets visual. It sets misleading. Because the truth is, gravity isn't really a force pulling you down. Not in the traditional sense. What you call falling is just following the straightest possible line through a curved reality. When you drop your pen, it isn't being yanked by some invisible hand toward Earth. It's moving forward in a warped geometry where straight leads down. And here's the strange part. If space can bend, so can time. You've already lived your whole life under the illusion that time flows evenly, but it doesn't. Not in a gravitational field. You've never stood on a truly flat plane, nor have you ever experienced perfectly uniform time, not even once. Near the Earth's surface, time ticks just slightly slower than it does in orbit. This isn't science fiction, this is GPS. The clocks aboard satellites must compensate for the fact that time literally moves faster up there. If they didn't, your location would be wrong by kilometers within hours. Einstein's general theory of relativity didn't just explain gravity, it shattered the notion that space and time are separate entities. They are one fabric, and massive objects like planets and stars are what distort that fabric. So gravity, as you feel it, isn't some mysterious glue or particle force. It's the result of space and time no longer playing fair. Now, rewind to Newton. In his model, gravity was a force, an attractive pull between any two objects with mass. The more massive they are, and the closer they are, the stronger the pull. This worked remarkably well for centuries. It explained planetary orbits, tides, and apples falling from trees. But it had a problem. Newton never knew how gravity worked. There was no medium, no explanation for what carried this force across empty space. He himself admitted it was a mystery. Einstein resolved that mystery, sort of. He said, "There is no force, only geometry. Earth doesn't orbit the sun because it's being pulled. It's moving in a straight line through a curved reality." But the trade-off for this insight was profound. If gravity isn't a force, but a byproduct of warped space-time, then it is not something we can block, shield, or switch off. It affects light. It slows time. It reaches across galaxies without a carrier. And yet, here comes the next twist. Some physicists are beginning to whisper, maybe even shout, that gravity is not fundamental at all. Maybe it's emergent, like temperature. Let that simmer. You know that temperature isn't a thing on its own. It emerges from the collective motion of countless molecules. Heat is not a particle, it is a pattern. Could gravity be the same? Could it be that what you perceive as space-time bending is simply the large-scale illusion of something deeper, more granular, more quantum? Think about that. What if, instead of gravity pulling you to the ground, it's information rearranging itself, and your body is just following the path that increases entropy? This might sound abstract, but it's not entirely crazy. We already suspect that black holes store information in surface area, not volume, a deeply unsettling idea that hints at a holographic universe. And in this framework, gravity is not a string pulling objects together, but the effect of a deeper statistical rule governing the way bits of information arrange themselves. Gravity, in this picture, becomes a shadow, a symptom, a trick of scale. If this idea holds, then we have to rethink everything. The curvature of space-time isn't the root of reality, but a large-scale approximation. Einstein's smooth, continuous fields might be like the surface of water, calm from afar but up close, teeming with chaotic molecules. And here's where it gets mind-bending. We don't yet have a complete theory of quantum gravity. That is, we don't know how to reconcile the elegant curvature of general relativity with the jittery chaos of the quantum world. One describes the very large, the other the very small, and they don't play nice. So you're left with this, a force that might not be a force, a pull that might be a push toward disorder, a constant inescapable sensation, your weight that might only exist because the universe is playing a trick of statistics on your atoms. Look around you. Everything is falling, slowly, steadily. Even the Earth is spiraling inward toward the sun, albeit over billions of years. Gravity is ever present, yet possibly illusory, not fake but secondary, a ripple of something deeper. You may never experience pure gravity, only its projection, like watching shadows flicker on the cave wall, thinking they are the real thing. What if the reason we've never found a graviton, the hypothetical quantum particle of gravity, is because it doesn't exist? What if we've been looking for the wrong thing in the wrong place? What if gravity is not in space, but what space does when it forgets it's empty? You think you're sitting still. Maybe you're lying in bed, eyes closed, mind drifting into cosmic theories. But your body is racing, orbiting, spinning, falling. The floor beneath you isn't solid ground in a fixed place. It's the surface of a planet spinning at over 1,000 miles per hour, hurtling around the sun at about 67,000 miles per hour, while the solar system itself is speeding through the galaxy at 500,000 miles per hour. And the galaxy? It's not stationary either. It's moving through the fabric of the universe at a speed too large to grasp. And yet, you feel none of it. Why? Because you're in freefall, constantly, perpetually, endlessly. If you were to stand on a bathroom scale, it would tell you your weight. It would press up against your feet and give you a number, but that number isn't telling you how much gravity is pulling you down. Not directly, it's telling you how hard the scale is pushing back. You aren't being pulled into the earth so much as you are being kept from continuing your fall through space. The surface you stand on is resisting your natural trajectory, that curved path through space-time. This is why astronauts in orbit appear weightless. They're not beyond gravity's reach. In fact, gravity is still acting on them almost as strongly as it does here on Earth. The difference? They're falling. So are you, but they're falling around the Earth, not into it. Their trajectory is perpetually curved by gravity, a perfect sideways fall that never hits the ground. And with no surface resisting their descent, they experience free fall as floating. You're doing the same thing right now, minus the floating gravity is constantly pulling everything toward everything else, and Earth is pulling you toward its center, but the floor stops you. The floor is what creates the illusion of weight. In a very real sense, gravity is the only force you can't feel directly. You feel your muscles, bones, skin, heartbeat. You feel wind, heat, motion. But you don't feel gravity itself. What you feel is resistance, friction, normal force. The universe is guiding you along a curved path, and solid objects interrupt it. Here sips as another illusion, up and down. There is no universal up. What feels like down to you is outward to someone on the other side of the planet. Space has no top or bottom. Down is just the direction in which space-time curves locally. If Earth were hollow and you dropped into the center, your weight would decrease the deeper you went, until, at the very center, you'd be weightless, pulled equally in all directions with no net force. You'd hover, not because gravity vanished, but because it cancelled itself out. Gravity is everywhere and nowhere. It's also relentless. You can't shield yourself from it. Electromagnetic forces can be blocked or redirected. You can wear Faraday cages, use lead walls, bounce light with mirrors. But gravity penetrates everything. The most massive bodies in the cosmos. Neutron stars, black holes don't contain gravity. They are gravity, focused into monstrous warps in space-time. And here's the kicker. The more mass you add, the more space-time bends, and the more you fall. Not because anything is pulling you, but because the floor just dropped a little farther beneath your feet. This is why time itself is distorted in the presence of mass. Clocks run slower the deeper they are in a gravity well. This is measurable, observable, and vital. Without accounting for this, GPS systems wouldn't work. Your smartphone's ability to guide you to a coffee shop depends on Einstein's math, on understanding that you are not standing still but being curved through time. And that brings us to black holes, the ultimate expression of falling. Imagine space so distorted, so deeply curved, that not even light can escape its grasp. Black holes aren't places. They're conditions, boundaries in space-time where the curve becomes infinite. If you were to fall into one, the journey would look different depending on where you're watching from. To you, as you cross the event horizon, time would seem to pass normally, though horrifyingly fast near the singularity. But to an outside observer, you'd appear frozen at the edge, red shifting into darkness, never quite falling in. Gravity isn't just a gentle slope. It's a cliff with an edge that tricks the eye, and beyond that edge, space-time itself caves inward. But here steps where illusion becomes terrifying. General relativity explains how gravity works, but not why. We know that massive bodies bend space-time. We've measured it. We've photographed the lensing of light around stars and galaxies. But what if this is just what gravity looks like from the outside? Inside, the truth might be weirder. Maybe space-time is not smooth. Maybe it's granular, foamy, pixelated at quantum scales. In this version, you're not moving smoothly down a slope. You're hopping from one chunk of space to another, following statistical rules, probabilities, constraints we don't yet understand. You feel continuous motion, but beneath that feeling is a staircase of probabilities. That's the goal of quantum gravity, to resolve the illusion, to show that falling is a higher-level description of a much messier reality, one where space-time is made of nodes, networks, strings, loops, one where the very concept of falling may not even exist. You feel like you're stuck to the ground, but maybe that feeling is nothing more than what happens when a set of rules emerges from chaos, when particles align their information in such a way that you experience direction, shape, location, and yes, gravity. So the next time you stand still, close your eyes. Remember, you're never still. You're always in motion, not because you chose to move, but because space itself doesn't hold still. You're tracing a line through a curved reality. You're being pulled not by a force, but by the nature of the fabric you walk on, and the direction you're being pulled is not down. Close your eyes. Not to sleep, not yet, but to reorient. To let go of everything you thought you knew about falling, pulling, weight, mass. You've been told since childhood that gravity is a force, that it pulls you downward, that it's what makes apples drop, oceans swell, and moons orbit. But what if nothing is being pulled at all? What if gravity is simply what happens when you try to move straight, and space itself won't let you? Let's revisit one of the most mind-warping ideas ever proposed. Gravity isn't a force, it's geometry. It means that being pressed into your seat in a rocket is indistinguishable from standing on Earth. It means that the force you feel on your body is not caused by some invisible hand yanking you down, but by the resistance of the floor beneath your feet. It's the path you follow when you try to move in a straight line through a warped fabric. A bowling ball on a trampoline is the metaphor most people use, but that image is deceptive. Space isn't being pushed down into something else. It's being curved within itself. Not in 3 dimensions, but in 4, because time bends too. You're not just moving through space, you're moving through space-time. And massive objects tell space-time how to curve. That curve tells you how to move. This is why the Earth orbits the Sun. Not because the Sun is tugging on Earth with a gravitational rope, but because the Earth is following the straightest possible path, a geodesic, through curved space-time. From Earth's perspective, it's simply gliding forward, but the path itself is bent. Imagine rolling a marble around the rim of a bowl. It's not turning of its own accord. The bowl shapes the motion. Here's the strange part. This geometric view of gravity has no force in the traditional sense. No carrier particle, no push, no pull, just shape. It's as if gravity doesn't want to be a force. It wants to remain a shadow, an illusion cast by deeper laws. Take Eric Valinde's entropic gravity, for example. In his model, gravity arises because matter disturbs the informational content of space. The pull we feel is actually a consequence of systems trying to maximize entropy, a cosmic version of probability, not mechanics. Objects move toward each other not because of attraction, but because it increases the total number of possible configurations in the system. It's a thermodynamic phenomenon masquerading as a force. Or consider holographic gravity. This theory suggests that everything happening inside a volume of space, including gravity, is actually encoded on a 2-dimensional boundary that surrounds it, like a cosmic projection. In this model, space-time itself isn't fundamental. It's a derived phenomenon, a side effect of quantum entanglement on the edge. You are living in the illusion of volume, of pull, of curve, but the real laws may lie elsewhere, on the boundaries. These are not fringe ideas. They are serious attempts to answer a persistent riddle. Why does gravity behave so differently from everything else? It's incredibly weak. A single magnet can overpower the gravitational pull of the entire Earth on a paperclip. It doesn't respond to shielding. It doesn't fit comfortably into quantum field theory. And it causes black holes, regions where space-time tears itself apart. Gravity plays by different rules, and perhaps it's because gravity isn't a rule at all, it's a pattern. And you, floating somewhere in that pattern, interpret it as weight, as inevitability. But even your own weight is not what you think. Your mass doesn't generate a pull. It tells space-time how much to curve around you. The Earth curves more. The Sun, far more still. But all of it is shape. You are not being pulled. You are following. Even light, massless, untouchable, bends to this illusion. When light passes near a massive object, it doesn't slow or twist. It simply travels straight, through a space-time that isn't straight anymore. That's gravitational lensing. That's the reason we can see galaxies stretched and duplicated behind other galaxies. Space-time bends and light obeys. And here sips a final thought to anchor you before we drift deeper. Then maybe nothing is truly solid. Not the ground beneath your feet, not the weight you carry, not even the pull you feel when you drop a stone into a pond. Maybe in the most literal sense imaginable, gravity is not pulling you down. It's set drawing you inward. You've always imagined escape as an upward motion, a rocket lifting off, a bird in flight, a balloon rising gently into the sky. But what if escape isn't about going up, but about slipping sideways through a trap you can't see? This is what escape velocity really is. Imagine you're standing on a perfectly smooth planet with no atmosphere, holding a baseball. You throw it as hard as you can. It arcs and falls back. You try harder, faster, and the ball travels farther, curves more gently, but still returns. Keep increasing the speed, and the arc becomes wider and wider until one day you throw it so fast, the curvature of its path matches the curvature of the planet. It never lands. It's in orbit. But that sip's not escape yet. Now go faster, faster still, until one day the ball's path no longer bends enough to stay near the surface. It keeps going. It's not that it's free of gravity. Gravity never turns off. It's just that its motion outpaces the downward curve of space beneath it. It's falling, but space is no longer catching up. That is escape velocity. For Earth, that magic number is about 11.2 kilometers per second, a speed that would hurl you from the blue marble's grasp into the emptiness beyond. Not because you overpowered a force, but because you outpaced a shape. Now take a moment to let this sink in. When you escape gravity, you aren't leaving it behind, you're moving through its warps in a way that never loops back. This is why gravity is not like a magnetic field or a spring. You don't flip a switch and turn it off. You can't shield yourself from it with a sheet of lead. You can't reverse its polarity. You can only move differently, faster, farther, on a path space itself won't bend back inward. And yet, even then, gravity chases you. The sun's gravity reaches well beyond Pluto. Its curve dominates our solar system, anchoring planets in elliptical orbits, pulling comets back from the distant Kuiper belt, stretching Oort cloud objects into frozen arcs that take millennia to return. And even farther out, the Milky Way's gravity whispers to rogue stars. Even galaxies feel the gravitational tides of one another. Clusters dance in webs, laced together not by visible strands, but by the hidden hand of mass-curving space over unimaginable distances. But here's the twist, one that continues to shake the foundations of physics. Galaxies rotate too fast. Their outer stars whip around at speeds that should fling them off into the void, unless there's more gravity than we can account for. But we don't see the mass. We don't detect the pullers. This is where dark matter enters, a placeholder for missing mass, an invisible presence inferred only by the gravity it seems to exert. We've never seen it. We've never touched it, and yet it appears to sculpt galaxies, anchor clusters, and define the scaffolding of the universe. But what if there is no dark matter? What if the problem isn't what's missing, but how we understand gravity? Some physicists propose that gravity doesn't behave the same at cosmic scales, that Newton's laws, and even Einstein's equations, might need adjusting when you move beyond solar systems into intergalactic realms. These are theories like Mund-modified Newtonian dynamics, which tweak the behavior of motion in low-acceleration environments, and others go deeper still, proposing that gravity is not a fundamental thing at all, that it is a side effect of quantum entanglement, of thermodynamic bookkeeping, of the way information organizes itself in the presence of mass and energy. In these views, escaping gravity might not even be possible, not because it's strong, but because it's entangled with the very rules of information itself. Even black holes, the ultimate trap, challenge our ideas of what it means to escape. According to general relativity, a black hole warps space-time so severely that beyond its event horizon, all paths, no matter how fast or how steep, curve inward. Light cannot escape. Time itself tilts into the hole, but quantum theory resists this finality. It whispers that information can never be truly lost, and so black holes must leak, must radiate, must evaporate. Stephen Hawking's famous radiation suggests that black holes aren't eternal, they can dissolve. But if that's true, where does the gravity go when the black hole vanishes? Does the curve of space flatten again, or was it always an illusion, a temporary configuration of information in disguise? So when rockets leave Earth, they aren't punching through an invisible wall. They are sliding out of a dip in a curve. They aren't fighting a force. They are navigating the shape of existence. And when satellites orbit, they are falling, endlessly falling, around the Earth, always missing, always chasing the horizon that curves away just fast enough to never be caught. So when you dream of escape, of leaving Earth, of floating free in the black, remember that gravity doesn't let go. It just stops catching up. You were born under gravity. You've never left it, not once. From the moment your lungs filled with air, to every footstep you've ever taken, your body has lived in the embrace of this pull. It shaped your bones, stretched your spine, kept your blood grounded. But more than your body, gravity has shaped your thoughts, and perhaps that's the greatest illusion of all. Because gravity is so constant, so omnipresent, it fades into the background. Like the hum of an air conditioner or the warmth of sunlight, you stop noticing it until you try to defy it. When a child drops a ball and watches it fall, they learn about gravity intuitively, not from equations, but from repetition. Objects fall. Things go down. The sky is up. The ground is down. These concepts become part of language, of metaphors. We say someone is downcast. A situation is weighty. Emotions are heavy. Success is uplifting. Our emotional and cognitive frameworks are laced with spatial metaphors drawn from our relationship with gravity. But this familiarity can also trap us, because what we feel doesn't always match what's real. Einstein's revelation was simple but profound. Gravity is not a force pulling downward. It is the result of following the straightest possible path through a space that's been bent. Let's unpack that. Imagine you're in deep space, far from any planet. You toss a ball, and it floats in a straight line forever. Now introduce a massive object, a planet, a star, and space-time around it bends. If you throw that same ball near the object, it still thinks it's moving in a straight line, but the space it moves through is no longer flat. The ball curves, not because it was pushed or pulled, but because the geometry of the universe around it has changed. That's why astronauts in orbit aren't floating. Because there's no gravity, they're falling constantly. They're in a continuous state of free fall, tracing a curved line through a curved space. Their stomachs don't feel gravity because the floor beneath them isn't resisting it. Even physicists, those fluent in equations and space-time metrics, struggle to unlearn the intuition of gravity as a force. It's embedded in how we simulate the world mentally. Drop a cup, it shatters. Jump off a step, you fall. The invisible pull is always there, or so it feels. So what happens when a concept is too familiar to be questioned? It becomes dangerous, because it blinds us to alternatives. Take Newton's gravity. A force between masses, works beautifully on human scales, predicts orbits, explains tides, but it assumes that action at a distance is instantaneous, that the Earth can feel the sun's gravity even before light from the sun arrives. Einstein shattered that idea. He made gravity local, a property of curved space-time, and in doing so he turned a mysterious pull into a warping of geometry. But what if even that is incomplete? Some modern physicists, like Eric Valindi, propose that gravity is not fundamental. It's not a property of matter or of space, but a result of entropy, of information rearranging itself. That gravity might be an emergent phenomenon, like temperature. That sip's unsettling, because it means we don't really understand gravity at all. We model it, we work with it. We can calculate the path of spacecraft to astonishing precision, but we might still be wrong about what it is. And the more we try to probe its source, the more elusive it becomes. We've tried to detect the graviton, the hypothetical quantum particle that would carry the gravitational force, Just as photons carry electromagnetism, so far nothing. We've built detectors so sensitive they can catch the tiniest ripples in space-time, gravitational waves from merging black holes, and yet gravity itself remains curiously immune to the rest of quantum mechanics. General relativity and quantum mechanics are two of the most successful theories in science. They both work, they both predict results with near-flawless accuracy, and yet they do not play well together. Gravity, the most familiar force we know, refuses to be tamed by quantum rules. That raises the possibility that gravity isn't a force at all. It's a story we tell, a description that works but not an explanation. And that seps where your mind stumbles. Because you don't experience space bending, you don't feel time slowing near a massive object. What you feel is heaviness, a pull, a direction. You interpret the world not through equations but through sensation. So we build narratives that match those sensations. We picture invisible arrows pointing downward. We imagine weight as an inherent property. But these are metaphors. Gravity may not pull at all. It may merely guide. Think of a marble rolling across a warped rubber sheet. The marble doesn't want to go toward the center. The sheet simply gives it no other option. That sips you. That sips everything. So maybe gravity is not an illusion in the sense that it doesn't exist, but in the sense that we've misunderstood what it really is. We've mistaken the feeling for the cause, the metaphor for the mechanism. And here's the final twist. The better our instruments become, the stranger gravity appears. It bends light. It slows time. It connects galaxies. It leaks energy. It may emerge from the shape of information itself. In short, gravity is not just a rule of the cosmos. It might be a reflection of how the cosmos keeps track of itself. Black holes are where gravity goes mad. They are not cosmic vacuums. They don't suck. They warp. They bend. They collapse the scaffolding of space and time inward until the laws we thought were permanent begin to fray. And even light, the fastest thing in the universe, cannot escape. To understand if gravity is an illusion, we must study its most extreme performance. And that means walking toward the edge of a black hole. You might expect something violent. Instead, from far away, it looks peaceful. A sphere of darkness, quietly holding the line where reality ends. The event horizon is that boundary, not a wall, not a surface, but a point of no return. Cross it, and the universe no longer lets you back out. It's a one-way door where even the idea of escape is forbidden. But from a scientific perspective, the most unsettling part is what happens before you even reach the edge. To an outside observer, someone falling toward the event horizon would appear to slow down, to freeze in place. They never seem to cross the threshold. Their light becomes redder, dimmer, until it fades. It's as if the black hole doesn't just trap matter, it traps moments. This is not special effects, it's relativity. Einstein's equations tell us that massive objects slow time, and black holes. They break it. So what does that say about gravity? It means gravity isn't just pulling things inward, it's changing the very way time flows. That's not a force, that's a rewrite of the rule book. And inside the event horizon? We don't know. Not really. The singularity at the core of a black hole, the point where all the mass has collapsed, isn't just dense. It sits undefined. Our equations yield infinities. That sits a polite way of saying, we don't know how to describe this. Physicists agree this can't be the full story. Somewhere in the overlap between general relativity and quantum mechanics, the illusion unravels. That's why black holes are the front line of modern physics. They reveal the limits of our understanding, and perhaps the lies we've been telling ourselves. Consider Hawking radiation. Stephen Hawking predicted that black holes should not be eternal. They should leak. Tiny quantum particles near the event horizon could be separated, one falling in, the other escaping, causing the black hole to lose mass over time. This evaporation is slow, almost poetic. A giant so powerful that it can devour stars might eventually fade into nothing. Some suggest the information is encoded on the surface of the event horizon. Others propose holographic models, where all the data inside the black hole is projected on its boundary, as if the universe is faking 3 dimensions, like a cosmic security hologram. And that brings us to the scariest idea of all. If gravity is just an emergent property, if it arises from the statistical arrangement of quantum information, then black holes aren't exceptions to gravity. They are explanations. They are where the illusion breaks down just enough to glimpse the wiring behind it. Black holes might not be holes at all, but seams, places where space-time folds back into itself like origami, places where the story of gravity becomes self-aware. Even more unsettling is the idea that every object, no matter how small, has its own gravitational field. You, me, every atom in your body. Right now, you are ever so slightly pulling the Earth toward you, and it, in turn, is pulling you back. That SEP's not a poetic metaphor. It's SEP's measurable. And it begs the question, is the universe built on pull or on participation? Maybe gravity isn't a ruler but a conversation, a way in which mass and space constantly renegotiate their relationship. You press into space and space responds, not just with force, but with shape, with time, with rules. And black holes are where that negotiation becomes unbearable, where the agreement collapses. They don't break the laws of physics. They expose the fine print. If we could decode them fully, not just their spin or their temperature, but their information content, we might learn that gravity doesn't come first in the chain of universal laws. It might come last, as an echo, a shadow cast by something deeper, something stranger. A simulation? A computation? A fabric woven not from particles but from logic? So when you look into the dark heart of a black hole, you are not staring at a monster. You are staring at the mirror of gravity, the place where our ideas fail, and the truth begins. And if gravity is an illusion, then the black hole is the magician's hand, daring you to see past the trick. To most of us, gravity feels like the most basic thing in the universe. Drop a ball, it falls. Step off a ledge, you fall. Planets orbit stars. Stars spiral in galaxies. Galaxies themselves form a cosmic web, all governed by gravity, right? But here's the strange truth. Of the 4 fundamental forces in physics, gravity is the weakest. Not just a little. Weaker by magnitude upon magnitude. The electromagnetic force, the one responsible for light, magnets, and the electricity powering your screen right now, is 10 to the times stronger than gravity. That's a 1 followed by 36 zeros. You don't notice this in daily life, because electromagnetic forces often cancel out. Your body doesn't fly apart, because the positive and negative charges in your atoms balance. But gravity, it doesn't cancel. It only attracts, and that makes it long-range and persistent. Still, why would the force that literally holds galaxies together be so puny? This is where the standard model of particle physics comes in, the framework we've used to explain all known particles and 3 of the 4 forces: electromagnetic, weak nuclear, and strong nuclear. It stuts not in the club. Despite decades of trying, physicists haven't been able to unify gravity with quantum mechanics. It stubbornly resists quantization, the process of describing a force as the exchange of discrete particles. In the electromagnetic field, photons carry force. In the strong force, gluons. In the weak force, W and Z, boluons. But for gravity, we've hypothesized a carrier, the graviton. The graviton has never been detected. No laboratory has captured it. No equation has pinned it down. It's a hypothetical ghost, a placeholder for a puzzle piece we haven't found. And maybe, just maybe, we never will. It could be a statistical byproduct of something deeper. the aggregate behavior of quantum fields, emerging only when large numbers of particles interact. This is the basis of several bold theories, including entropic gravity, proposed by physicist Eric Valindi. Entropic gravity imagines space as an information storage system. Mass doesn't bend space directly. Instead, the presence of mass changes the information density of space, creating what we interpret as gravitational attraction. It's not a force pulling objects. Imagine a crowd gathering around a fire. The warmth spreads, the arrangement of people changes to accommodate the energy distribution. No single person is pulling the others, but the overall pattern emerges from basic rules. That, Valindi argues, is gravity. It's such not a command from nature. It's such a consensus. If this is true, then gravity is not real in the way we thought. It's not a fundamental actor, but a macro illusion formed from micro-truths. And yet, the illusion works beautifully. Our GPS satellites must account for general relativity to provide accurate positioning. The trajectory of spacecraft, the orbits of moons, the tides of Earth, all rely on gravity behaving consistently. But does that make it real? It's like watching a flock of birds move in perfect unison. To the eye, it's a single creature, but up close it's just individuals following simple rules. The illusion of a being is created by emergent behavior. Gravity may be the same. An elegant lie told by the universe to make things calculable. In the realm of quantum mechanics, forces behave probabilistically. A particle's position, speed, and spin aren't fixed until observed. It's all fuzz and uncertainty. But gravity behaves classically, smoothly, predictably. Bridging these two realities, quantum fuzz and gravitational certainty, is the holy grail of physics. String theory tries to do this by proposing that all particles are actually vibrating one-dimensional strings. Different vibrations equal different particles. Gravity emerges naturally in string theory as one possible vibrational mode, the graviton again, but now with mathematical support. Another contender is loop quantum gravity, which ditches string theory entirely and instead attempts to quantize space itself. In this view, space is not continuous but made of discrete loops, tiny, indivisible units of area and volume. Gravity then arises from how these loops interlock and evolve. But neither theory is complete. Both are riddled with problems, assumptions, and untestable predictions, at least with our current tools. And that leaves us in limbo. Gravity continues to dominate our cosmic choreography, bending starlight, dancing with galaxies, quietly pulling the curtain across the visible universe. But behind the scenes, its nature remains suspicious. Consider this. We've never observed gravity on the Planck scale, the smallest measurable length where quantum effects dominate. In fact, gravity is millions of times weaker than anything we've tested at that level. Some physicists wonder, what if gravity doesn't even exist at that scale? What if it sets a purely macroscopic illusion? That would mean that the further down we look, into atoms, quarks, strings, code, the less gravity matters, until finally we reach a floor where there is no curve, no pull, no warping, just information, just probabilities, just raw being. That would turn our entire view of the cosmos inside out. It would mean gravity is not the stage, but the story, a narrative the universe tells to organize itself. We thought gravity was the script. It might just be the summary. And if that's true, then understanding gravity won't just help us understand motion or matter. It will help us understand why there is any story at all. Every generation has dreamed of it. Anti-gravity. It's one of the most enduring fantasies in science fiction. Starships that hum quietly above the ground, hoverboards skating on invisible force fields, buildings suspended in the sky. Even today, the word anti-gravity sparks a flicker of hope, a whisper that maybe, just maybe, will break the rules of nature and rewrite the sky. But what does science say? Is anti-gravity even possible? Or Are we chasing a ghost that was never there to begin with? Let's start with the basics. Gravity, as we experience it, only attracts. It pulls masses toward each other. Unlike electromagnetism, which has positive and negative charges, gravity has no opposite. There's no negative mass in our observable universe, no repelling gravity, just pull. So for anti-gravity to exist, we need something that either cancels out gravitational pull or creates repulsion, the way two like-charged magnets push away from each other. Mainstream physics gives us no verified mechanism for either. But the loopholes are interesting. In 1917, Einstein introduced something into his equations of general relativity that would later come back to haunt and intrigue physicists: the cosmological constant. He added it to counteract gravity, allowing for a static universe. He didn't know yet that the universe was expanding. When expansion was later confirmed, he called it his greatest blunder. But was it? Today, the cosmological constant has been reimagined as a form of dark energy, the mysterious force causing the expansion of the universe to accelerate. And here sits the kicker. Dark energy has anti-gravitational properties. It doesn't detract. It repels. It stretches space itself, pushing galaxies apart faster and faster. It's not anti-gravity in the jetpack sense, but it's the first real evidence of repulsive gravity on a cosmic scale. So why can we bottle that? Why can't we build a dark energy engine and soar above the clouds? Because dark energy doesn't play by the same rules. It's not a force we can harness with wires or magnets. It's woven into the fabric of space-time, like a gentle wind blowing between the atoms of the cosmos. It's everywhere, but not in a usable form, at least not yet. Still, scientists have tried other ways. One idea comes from exotic matter, theoretical stuff that has negative mass, not like -5 kilograms, but a property that would cause it to react opposite to normal matter. If you pushed it, it would accelerate toward you. If placed near positive mass, it would move away, not due to active repulsion, but due to the oddities of how space-time would curve around it. If we could create or harness negative mass, some theorists believe we could construct stable wormholes or warp drives, bending space around us rather than moving through it. But again, there sits a problem. We've never observed exotic matter, and even if it exists, the quantities needed are, at this stage, cosmically impractical. In the 1990s, Russian scientist Eugene Podkletnov claimed to have created a gravity shielding device using spinning superconductors. His work was controversial, difficult to replicate, and ultimately dismissed by most of the scientific community, but it sparked a wave of interest. NASA for a while had a small research project under the Advanced Propulsion Physics program, also known as Breakthrough Propulsion Physics, to explore the possibilities. But no breakthrough ever came. So where does that leave us? Floating in the in-between. On one side, rigorous physics telling us anti-gravity isn't possible. On the other, hopeful anomalies and tantalizing theories suggesting we just haven't looked at it right. And maybe, like with many things in physics, the question isn't is anti-gravity possible? Because if gravity is an illusion, an emergent force, a statistical effect, a thermodynamic artifact, then maybe there's a way to rearrange the variables and produce a different outcome. Maybe it's not about creating an opposite force, but rather about changing the conditions so gravity doesn't act the way it usually does. Think about buoyancy. A balloon filled with helium doesn't defy gravity. It obeys the rules of fluid displacement. It rises because it's lighter than the surrounding air. In a sense, it's an illusion of anti-gravity, but really, it's a rebalancing of forces. That turns the dream. And it's one worth dreaming. Not because it promises flying cars or moon elevators, but because it challenges us to question the default rules we've accepted since childhood. Apple falls. sky holds, ground is ground, up is up. But none of that is fundamental. It sets just the setting of the simulation. And if we find the code that creates gravity, maybe we'll also find the key to rewriting it. Until then, we continue to test, tinker, and ask questions, because anti-gravity may not exist yet. But the human mind, curious, irreverent, and wildly imaginative, has always had a kind of weightlessness of its own. Let's shrink, down past the grains of sand, past the cells, the molecules, the atoms, down to the realm where the very concept of down begins to lose its meaning. This is the quantum scale, the world of particles, fields, uncertainties, and rules that seem designed not to be understood. Here, gravity behaves like a ghost. Let's put that into perspective. The electromagnetic force between a proton and an electron is about 10 stronger than their gravitational attraction. That 10's a 1 followed by 36 zeros, enough to make you wonder, why is gravity so weak? It shapes planets, stars, galaxies, and the universe, but it barely nudges a single electron. This imbalance is known as the hierarchy problem, and it's one of the biggest unresolved mysteries in theoretical physics. Why is gravity such a feeble player in the quantum orchestra? One answer may lie in extra dimensions. Some string theorists suggest that gravity leaks into other spatial dimensions, while electromagnetism and the nuclear forces are confined to our familiar 3D world. Gravity might be diffused through additional invisible dimensions, making it seem weaker here than it actually is. Imagine a showerhead spraying water into a thin line versus one dispersing water in every direction. The second looks weaker at any one point, not because it is, but because it's spread out. This gives rise to another idea. Maybe gravity is not fundamental at all. Maybe it's emergent. This brings us to the mind-bending theories of physicist Eric Verlinde, who proposed that gravity might arise from entropic forces, that is, from the tendency of systems to move toward greater disorder. In this view, gravity isn't a fundamental force like electromagnetism. Instead, it's a macroscopic statistical effect, much like how temperature is the average motion of molecules. In Verlinde's model, gravity emerges from information encoded on holographic surfaces. Matter bends spacetime not because it exerts a force, but because the information content of space is shifting toward greater entropy. This would mean that gravity is not real in the same way light or magnetism is. It's more like an illusion, a byproduct of how information organizes itself in the quantum vacuum. Now pause here. What does it mean if mass doesn't pull on space-time, but instead space rearranges itself around clusters of information? It means that falling isn't about weight or force, but about the universe resolving equations of entropy. And if that's true, then gravity is like a language, not a push, not a pull, but a narrative that the universe tells to itself as things change shape and position. But how do we test this? That's where things get tricky. The quantum world is ruled by probabilities, wave functions, and measurement. To observe something at that scale is to change it, and gravity, being so weak at this level, is incredibly difficult to detect in quantum experiments. Still, a few tantalizing efforts have been made. In 2021, 2 teams of scientists proposed an experiment that might detect quantum entanglement caused by gravity. If successful, this would suggest that gravity, usually seen as a classical force, has quantum properties. It would also imply something even weirder, that gravity can cause entanglement, which might mean gravity itself is entangled across space-time. Entangled gravity. Not just particles mirroring each other, but the very curves of space linked invisibly across time. You begin to see why so many physicists think gravity isn't a thing. It's a relationship, a relational structure built on geometry, entropy, and probability. So what's the implication? If gravity doesn't exist in the way we think, if it's emergent, informational, or statistical, then maybe it can be reprogrammed. Just like we reprogram matter with temperature, or light with optics, or particles with magnetism, maybe the fabric of gravity can be bent, not by brute mass, but by informational architecture. Imagine floating not because you cancel gravity, but because you've rearranged the underlying narrative of that space. Suddenly, anti-gravity becomes less about force and more about persuasion, less about breaking the laws and more about offering space a different story to tell. That is where the illusion of gravity becomes powerful. The world of quarks, photons, entanglement and uncertainty. And we realize something profound. If gravity can emerge from quantum processes, then our entire understanding of reality is stitched together by phenomena that do not obey force but pattern. And if we can find the pattern, we might just float. Imagine lying down in a dark, quiet room and stretching your arms wide over a perfectly smooth, invisible surface. You feel no edges, no folds, nothing pushing back. That's space-time, or rather, how we often conceptualize it. An invisible backdrop, a perfect passive stage upon which the universe plays out its drama. But what if this stage isn't real in the way we think it is? What if space-time itself, the very thing that gives rise to the illusion of gravity, isn't a fixed canvas, but something that bubbles up from deeper hidden ingredients? In recent years, a provocative idea has begun to take hold in certain corners of theoretical physics. It suggests that space-time is not fundamental. Instead, it may be emergent, a construct that arises from something else entirely. Think of how a mirage appears on hot asphalt. You see water, but there is none. The shimmering distortion is real, but it's not a pool. It's a consequence of underlying physics. Now imagine gravity and space-time are just as deceptive. This theory doesn't come from nowhere. It emerges from puzzles that traditional physics has struggled to solve, especially in reconciling general relativity with quantum mechanics. These two pillars of modern physics explain the universe beautifully separately. General relativity governs the grand ballet of stars and galaxies, while quantum mechanics rules the jittery dance of particles. But try to blend the two together, and you're met with paradoxes and infinities. That's where the idea of emergent space-time comes in, a possible bridge. Let's pause for a moment and consider a fascinating proposal, the ER=EPR conjecture. It suggests that space-time connectivity, like wormholes, Einstein-Rosen bridges, is fundamentally linked to quantum entanglement, Einstein-Podolsky-Rosen pairs. In other words, space-time itself might be the result of entangled quantum states. No entanglement, no space, no time. You wouldn't fall because there'd be no down to begin with. That's not a metaphor. That's the claim. It's wild, yes, but also grounded in serious math. Take the work of Juan Maldacena, who introduced a framework known as AD-CF-CFT correspondence. This has led many to speculate if gravity and space can be encoded holographically, then they aren't fundamental, they're emergent. Which brings us to another intriguing idea, entropic gravity. You may remember this from earlier. Now, sit with that for a second. But if space and time aren't real, what is? That question doesn't have a satisfying answer yet. The best candidates are abstract, mathematical structures like tensors, entangled networks, or even computational systems. Some physicists believe reality might be a quantum computer running a code so fine-grained, we mistake it for existence. In this view, we aren't in space. We're made of computations that give rise to the illusion of space. That includes planets, apples, and yes, gravity. In fact, some theories suggest space-time could emerge from entanglement patterns the way a woven cloth emerges from threads. No single thread defines the fabric. It's the relations between them that make the cloth. Remove the relationships, and the fabric vanishes. And so here you are, lying in your bed, wondering if the mattress beneath you exists in any meaningful way. If your body is suspended in a web of quantum relations that merely feels like space. If the thing you call gravity is just the lowest energy path through an informational haze. Maybe it is. Maybe it is. Certes. But the idea that space-time could be an illusion doesn't make the world less beautiful. In fact, it might make it even more miraculous, because it means that reality as you experience it, sitting on a planet held to the ground by what you once thought was a force, may be a kind of cosmic trick. Not a malicious one, just a useful one. A gentle lie told by the universe to help you navigate its vast and intricate dream. And dreams, as you know, can feel very real while you're in them. What if everything you've ever felt, your weight against the floor, the drop in your stomach on a roller coaster, the gentle tug that keeps oceans loyal to the earth, was never real to begin with? Not in a metaphorical way, not in a gravity is weird kind of way, but truly, literally not real. A fabrication, a script playing out inside a much larger illusion. This is the core of one of the boldest ideas to emerge from theoretical physics and simulation theory, that gravity, as we know it, could be an emulated experience inside a constructed environment. A physics engine, not a physical force. A line of code, not a curvature of space. Let it slow that down. In such a world, gravity wouldn't need to be explained through particles like the graviton or distortions in a four-dimensional fabric. It would be a rule baked into the simulation, a logic constraint. Let's use an example. Modern physics simulations can model galaxies, stars, planetary orbits, and gravitational lensing without actually creating gravity. They just emulate it through calculations and code. Some theorists have pointed to strange glitches in our universe as possible evidence for such emulated gravity. Quantum entanglement, for example, which seems to bypass the speed of light limitation, or dark energy, an unknown force accelerating the expansion of the universe without clear cause, or even cosmic censorship and the mysterious nature of black holes. Could these be artifacts of a simulation rendering gravity in ways we don't fully understand? Here's another angle. In video games, the physics engine doesn't model every atom. It cheats. It uses approximation, probability, and procedural tricks. Could our universe be doing the same? What if black holes are loading boundaries? What if quantum uncertainty is a compression algorithm? What if gravity is just one of the illusion's most efficient shortcuts? A way to ensure objects behave without wasting unnecessary computation. Now, we've drifted into speculation, but not into nonsense. Simulated gravity could explain many of the puzzles physics hasn't yet cracked. Why gravity is so weak compared to other forces, why it's impossible to quantize, why it feels like a fundamental part of reality, but evades all attempts at true unification. It also introduces new philosophical implications. If gravity is simulated, then so is mass, so is inertia, so is the floor beneath your feet. And if the illusion is that complete, what part of you isn't part of it? Where is the edge of the lie? Of course, the simulation hypothesis can't be tested directly, at least not with current tools. But some scientists have proposed indirect evidence, like limits on the precision of space-time or anisotropies in cosmic radiation that resemble rendering artifacts. Even if those leads go nowhere, the idea serves a valuable purpose. It challenges us to look at gravity not just as a mystery to solve, but as a signal, a sign that what we think is fundamental may be only a convincing performance. And so, next time you drop something, your phone, your keys, your belief in reality, remember this. Gravity may not be pulling you down. It may just be telling you a story that keeps you grounded, so you don't ask the question that really matters. Who or what is pressing play? But gravity stubbornly resists this neat categorization. It's the only fundamental interaction for which no carrier particle has ever been discovered, and this absence has haunted physicists for decades. The theorized particle, of course, is the graviton, a massless spin-2 boson that should, in theory, carry the gravitational force in a quantum framework. It's been predicted, imagined, and baked into dozens of models. But no experiment has ever seen one. Not directly, not indirectly, not even a whisper. Why does that matter? Because if gravity were like the other forces, we should have at least seen its quantum fingerprints, especially in high-energy collisions, or in the cosmic microwave background, or through some distortion in known particle behavior. But instead, gravity remains oddly mute. This leads to one of the strangest possibilities in all of modern physics, that gravity doesn't need a particle at all, that it operates in a different way, not as a force transmitted through space, but as something else entirely. Einstein, remember, didn't describe gravity as a force. He described it as geometry, the shape of space-time itself. In his view, matter bends space, and objects follow those bends. No particles required, just curves and motion. This friction is what gave rise to string theory, an attempt to unify gravity with the other forces under a common framework. And yes, in string theory, gravitons emerge naturally as vibrations of a closed string. But again, no proof, no detection, no gravitational scattering events, no signal. And so the question returns, if gravity exists, and clearly it does, but has no messenger, what does that say about the universe itself? Some have proposed that gravity might be emergent, that it arises not from particles, but from the collective behavior of something deeper. Think of temperature. You can't isolate a temperature particle. It's a statistical outcome of many moving parts. What if gravity is like that? A side effect of information flow, or quantum entanglement, or holographic surfaces processing bits? This is more than just philosophical musing. The holographic principle, first proposed in black hole thermodynamics, and later expanded by researchers like Leonard Susskind and Juan Maldacena, suggests that gravity in 3 dimensions may emerge from information encoded on a 2-dimensional surface, like a cosmic projector screen. In this view, the force we feel isn't real in the particle sense. It's the result of deeper calculations, correlations, or entropic shifts. The graviton never arrives, because it was never needed. It may also explain why we haven't detected gravitational waves at the quantum level, because the granularity of gravity might be inherently incompatible with particle-based detection methods. Still, not all physicists are on board. The search for gravitons continues. Experiments like LIGO and LISA are pushing boundaries, hoping to detect ever fainter ripples in space-time. Maybe one day we'll catch a glimpse, but until then, gravity stands alone, a force without a carrier, a law without a messenger. And that makes it suspicious. Because in nature, patterns point to truth, and when one pattern refuses to match the rest, it could mean we've misunderstood the whole game. Perhaps it simply is. And perhaps that sits the most radical idea of all. Imagine you're holding a snow globe. Inside a tiny winter village, frozen streets, falling snow, a train circling a hill. Now imagine that everything happening inside that globe, the entire 3-dimensional scene, is actually encoded not inside but on the surface of the glass. This is the core of the holographic gravity hypothesis. At first it sounds like science fiction, but in the strange intersection between gravity and quantum theory, it's one of the most serious proposals on the table, a radical reframing of what space, time, and gravity really are. The origin of the idea, the seeds of this theory were planted not by cosmologists gazing at galaxies, but by physicists studying black holes, specifically by Jacob Bekenstein and Stephen Hawking in the 1970s. They discovered something strange. The entropy of a black hole, the amount of information needed to describe what's inside it, didn't scale with the volume of the black hole, it scaled with the surface area. That was shocking. In normal physics, if you double the volume of a room, you double the number of atoms, the amount of energy, and the entropy. But for black holes, it was the event horizon, the boundary, that held the information. This hinted at something deeper. Maybe space and information aren't stored where we think. maybe what happens inside the universe is actually determined by what's happening on the edge. All the information contained in a volume of space can be represented as a theory on the boundary of that space, like a hologram, a flat image that creates a three-dimensional illusion. Enter gravity. So what does this have to do with gravity? Everything. In 1997, physicist wildest proposed a duality known as ad-CFT correspondence. He showed that a type of string theory operating in a higher dimensional space with gravity called anti-de Sitter space could be exactly equivalent to a quantum field theory without gravity on the lower dimensional boundary. In other words, a universe with gravity equals a universe without gravity as long as one is projected from the other. You think you're feeling gravity? You might just be experiencing the output of a cosmic computation happening on the edges of the universe. The implications. If the holographic principle is correct, it has massive implications. Space and time aren't real in themselves. They're emergent constructs from deeper information dynamics. Gravity isn't a force, nor is it a field. It's a side effect of how information is arranged at the universe's boundaries. The entire universe might be a projection, not in the matrix sense, but in a mathematically precise way. And it might explain why gravity resists quantization. If it's not fundamental, it doesn't need a graviton. It doesn't need quantum fields. Gravity is the illusion, not in the sense of being fake, but in the sense of being secondary. Entropic gravity. Building on this, physicist Eric Verlinde proposed the concept of entropic gravity. He suggested that gravity arises from the tendency of systems to maximize entropy, a thermodynamic effect, not a true force. Imagine a droplet of ink dispersing in water. It spreads not because it's pushed to, but because the system moves toward higher entropy. Verlinde claims gravity works the same way. Particles don't fall because they're pulled. They fall because the universe is trying to balance its informational books. Testing the theory. Scientists are examining gravitational lensing in galaxies, looking for deviations from Einstein's predictions that might point to emergent gravity. Others are trying to find quantum analogues of spacetime emergence in condensed matter systems. Theoretical work is exploring whether the structure of spacetime itself acts like a quantum error-correcting code, preserving the data of reality. None of this is easy. The holographic universe isn't something we can just look at. It hides its machinery behind equations, not levers. But the pieces are adding up. A universe on the edge. Imagine that every atom, every movement, every thought you've ever had is a shadow of data rippling across a boundary you can't see. Imagine that time itself is just a way for this information to unfold. In this view, the stars aren't just burning gas. They are solutions to equations written in light, projected inward from a cosmic edge. The pull you feel toward the Earth isn't a tug, it's an algorithm. You are falling toward entropy. Why? It feels so real. But it also changes everything. Identity, memory, causality. Maybe we are the holograms. The universe might be simpler than it appears, or more complex than we can ever imagine, or, perhaps most likely, both. It becomes poetry, written on the surface of forever. Zoom in, closer, closer still, past the molecules, the atoms, the electrons spinning like wild ideas around protons. Keep going, past the quarks, past the energy fluctuations, past the boundaries of everything we understand. Eventually you reach a realm that doesn't even behave like space anymore. It bubbles, it twists, it froths. This is quantum foam, a concept proposed by physicist John Archibald Wheeler to describe the very smallest scale of the universe, the Planck length, about 1.6 x 10⁻⁻⁰ meters. At this scale, space and time are not smooth. They are wild, frenzied, continuously fluctuating. They don't behave like a stage upon which physics unfolds. They are the drama itself. Let's dive into this seething madness. What is quantum foam? But on the tiniest scales, far, far beyond what we can observe, that ocean becomes a storm. Due to Heisenberg's uncertainty principle, energy and position cannot both be known precisely. So even empty space isn't really empty. Virtual particles pop in and out of existence. Energies fluctuate wildly. Curvatures appear and vanish. The result? Space-time looks more like foam than fabric. Not made of bubbles in the classical sense, but full of fluctuations in geometry, topology, and energy. But always bubbling, always uncertain. Why does this matter? Quantum foam could be the foundation of everything. It could explain how particles emerge. It might reveal why space-time is curved at larger scales. It could be the link between quantum mechanics and general relativity. Because here sips the truth. Gravity, which is about the curvature of space-time, must emerge from what space-time is made of. And if space-time isn't continuous but quantized, then its granularity may be key to everything. Imagine trying to understand ocean waves without knowing that water is made of molecules. We're in a similar position. To understand the ripples of gravity, we must first understand the grains of space-time. Is space-time digital? One of the most profound implications of quantum foam is the possibility that space-time is discrete, made up of indivisible bits like pixels on a screen. This idea is central to loop quantum gravity, a theory that attempts to quantize space-time itself. Instead of a smooth continuum, space is made up of tiny loops or spin networks that evolve over time into spin foams. These aren't visual loops you could see, but mathematical structures that describe how volumes and areas are quantized. This would mean there is a smallest possible length. No measurement can be made more precise than the Planck scale. Space-time is like a quantum Lego set, and the foam is the infinite shaking of those bricks at the foundation. Does foam explain the weirdness? Many strange phenomena in physics begin to make more sense in this context. Why does the vacuum have energy? Because it's not empty, it's full of fluctuations. Why is space expanding? Maybe the foam itself is inflating, its own structure producing expansion from within. Why does time flow? Maybe it doesn't. Maybe the foam just rearranges itself constantly, giving us the illusion of sequence. Detecting the undetectable. Now for the big question, can we ever observe this foam? Directly? Probably not. The Planck length is absurdly small, far smaller than any current or planned experiment can reach. But there may be indirect clues. Photon dispersion. If quantum foam affects light, photons from distant sources like gamma-ray bursts might arrive at slightly different times depending on their energies. Noise in gravitational wave detectors. Some physicists suggest that unexplained background noise might be a sign of space-time jittering at the smallest scales. Quantum gravity effects near black holes. Subtle deviations from classical predictions might hint at the underlying foam. It's like trying to study a beach by watching the shimmer in the distance. You can't see the grains directly, but you can see the pattern they produce. Theoretical playground. Quantum foam is not just a frontier, it's a playground. It's where string theory, loop quantum gravity, and causal set theory all fight for dominance. Some think the foam is made of vibrating strings. Others believe it sups a spin network. Still others think space-time events are connected only by cause and effect, a cosmic web of logic, not geometry. No one agrees, but everyone suspects the answer lies here, the edge of comprehension. Maybe distance, location, and time are secondary traits, born from how information dances at the smallest scale. In that case, quantum foam is not just real, it's everything. The root of time, the soil from which reality grows. And perhaps, just perhaps, the next great revolution in science will come not from looking up, but from peering inward, into the depths, into the froth. You wake up one day with a thought too strange to dismiss. What if everything you've ever known, every law of nature, every falling apple, every orbiting moon is just code? This is the simulation hypothesis, the increasingly serious idea that reality as we experience it might not be base reality at all, but an incredibly detailed artificial construct, like a video game running on an unimaginably advanced computer. It sounds like science fiction, but many physicists, philosophers, and technologists believe it's not only possible, but statistically likely. And strangely enough, gravity may be the key that ties the whole idea together. Let sex fall down this rabbit hole carefully. Are we living in a simulation? The simulation hypothesis is most popularly associated with philosopher Nick Bostrom, who in 2003 proposed a trilemma. Almost all civilizations destroy themselves before reaching technological maturity. Advanced civilizations don't care to simulate ancestral lives. We are almost certainly living in a simulation. Bostrom argues that if even one civilization becomes technologically capable of simulating reality at a planetary or universal scale, and chooses to do so, then the number of simulated beings would vastly outnumber real beings. Gravity is a rendering shortcut. In video games and simulations, not everything is calculated all the time. That would waste resources. Instead, environments are rendered only when observed, and with the least complexity required to make them look real. Now think of quantum physics. Particles that exist in multiple states until observed. Sound familiar? But what about gravity? Gravity, in this view, may not be a fundamental force. It might be a shortcut, a computational trick designed to conserve processing power in a simulation. Instead of calculating every interaction between particles, simulate a smooth curve spacetime. Instead of tracking forces individually, just calculate local weight based on proximity to mass. This idea that gravity is emergent, not fundamental, isn't just fringe simulation talk. It's also the conclusion of many respected physicists. Emergent gravity in the code of the cosmos. Dutch physicist Erik Verlinde proposed in 2011 that gravity is not a fundamental force at all. Instead, it's an emergent phenomenon, a byproduct of entropy and information theory. In other words, gravity equals sign information organization. This closely mirrors how video games simulate physical interactions by calculating changes in data over time. If gravity isn't set to force, but an emergent effect of how information is distributed across space, then spacetime itself might be a projection, a hologram of deeper information-based laws. And that hologram might be the rendered interface of the simulation we're in. Quantum limits equal sign processing limits? Let's consider some strange coincidences. Speed of light. Nothing travels faster. Could this be the processing limit of the simulation engine? Planck length. The smallest meaningful measurement. Could this be the pixel size of the simulation? Quantum uncertainty. You can't know both position and momentum. Could this be intentional compression of data to save processing power? Even vacuum fluctuations, the bubbling of quantum foam, might be interpreted as background computational noise. The deeper we look, the more reality seems built from bits, not atoms, bits of information. There are even anomalies in gravity that, if not explained by dark matter or modified theories, might point to something. In some simulations, objects can behave unexpectedly when the processing load is high. Galaxies spin faster than they should. Are we watching gravitational approximations struggling at the cosmic scale? Quantum entanglement seems instantaneous, while gravity seems bound by speed. Could these be two different layers of code, one local, one networked? While speculative, this raises a disturbing question. If gravity is a shortcut, what happens when the program lags? Consciousness and observer effects. Now let's bring consciousness into the mix. Quantum experiments show that observation collapses probability into reality. But what qualifies as an observer? A machine? A human brain? A conscious mind? Some theorists argue that consciousness is the user interface for the simulation, a way for the simulation to become aware of itself through you. In this framework, gravity might only emerge in the presence of observation, just like simulated shadows only appear once the camera faces them in a video game. Gravity is in set pulling you down. So, are we trapped? Let's suppose we are in a simulation. It's not an inescapable force, but a programmable rule. It might be tunable, adjustable, even breakable under certain conditions. If we find the underlying logic, we might one day manipulate it, not by counterforce, but by understanding the code. And if that sits true, then the next era of science won't be about energy or particles or telescopes. It'll be about reverse engineering the simulation, finding the seams, exploiting the shortcuts, discovering the source. Gravity, then, isn't just a force. It's a breadcrumb, a hint, maybe the first clue in understanding not what the universe is, but why it was made. What if gravity isn't just a silent backdrop? What if it sits listening? We often think of the universe as cold, impersonal, a series of laws playing out mechanically across space and time. But there sips a growing body of thought, both spiritual and scientific, that suggests something profoundly different, that the universe is not only aware of itself, and once again, gravity may not be just a force. It might be a function of consciousness. Let's explore a radical but increasingly whispered question. What if gravity is a form of attention? The observer problem, revisited. Particles remain in a state of probabilistic superposition until they're observed. Once observed by a machine, a photon, or a mind, they collapse into a definite state. Why? No one knows. What if macroscopic reality is stabilized by the continuous presence of observation? What if the fabric of the universe only maintains its coherent structure because it's being watched from within? Gravity might not just be pulling you down, it might be holding you in place because it knows you're there. Gravity and the act of noticing. Every day, without thinking, you interact with gravity. You stand, sit, move, without questioning it. But have you ever noticed that gravity behaves as though it knows exactly where you are? No delay, no uncertainty, instant and continuous spatial alignment. This silent responsiveness feels different from other forces. Electricity crackles, magnetism pulses, but gravity simply attends. It is always calibrated, always consistent, always watching. Theoretical physicist John Wheeler once suggested a powerful idea. The universe does not exist unless it is observed. Now imagine a universe in which observation isn't passive, but structural, where gravity isn't just reacting to mass, but to awareness itself, the consciousness field hypothesis. Now, combine that with gravity. Could gravity be the field that connects these flickers? The thread that knits awareness together into the experience of reality? If so, gravity wouldn't just be spatial, it would be cognitive. A unifying field that organizes not only objects but perceptions. Wherever there is gravity, there is a framework that supports experience. Evidence in the brain? Here's where things get even stranger. Recent neuroscientific studies show that consciousness may emerge not from any one part of the brain, but from the synchronization of activity across distributed areas. These synchronizations rely on waveforms, rhythms that are disturbingly similar to gravitational resonances. Furthermore, consciousness has a location. It seems to center in the body, despite being formed across the brain. This centering is a gravitational-like experience. You feel grounded, centered, anchored. Could gravity in the brain be more than a background force? Could it be the very architecture of self-awareness? For centuries, mystics and philosophers have described the universe as a single living mind. In Hinduism, the concept of Brahman, the universe as consciousness. In Kabbalistic teachings, reality is a cascade from pure awareness into physical form. In Gnostic traditions, the material world is a thought. Now, modern cosmology begins to echo these ideas, not in mythic terms but in equations and paradoxes. When gravity bends light, it acts like a lens. When it warps time, it manipulates experience. It doesn't just move objects. It shapes how we perceive them. It doesn't just hold galaxies together. It may hold stories, selves, and sensations together. You, the gravity point. You are, in a strange way, the center of your own observable universe. Not metaphorically, literally. From your perspective, every galaxy expands away from you. Every gravitational pull is measured from where you stand. And yet, so is everyone else's. This isn't sit ego, it's sit physics. It suggests that each observer recenters the cosmos, recalculates its curves, remeasures its warps. Gravity responds to you as if it knows you're watching. And perhaps it's not a glitch. If gravity is aware, what now? Let's ask the unaskable. If reality is structured by observation, if consciousness is the input that holds space together, then the universe is not indifferent. It sits engaged. Every time you think, perceive, feel, you see not just experiencing the universe, you are completing it. It may be the invisible language in which that knowing is written. Let's turn the question upside down. We know that gravity bends time, but what if it also builds it? For most of scientific history, gravity has been treated as something that acts within time, a force with a duration, a direction, and a history. Planets orbit for centuries, stars collapse over eons, black holes form over billions of years. Time, in this view, is the passive backdrop, gravity the dancer on its stage. But what if that assumption is backwards? What if gravity doesn't just move through time, but actually sculpts it? Einstein sets time-warping legacy. Start with Einstein. His theory of general relativity shattered Newton's tidy framework. Time, once thought to be an absolute ticking clock for the entire universe, turned out to be fluid, deformable, elastic. Time moves slower in stronger gravitational fields. Clocks tick more slowly on Earth than they do in orbit. The GPS in your phone corrects for this difference every second of every day. In short, gravity affects time. But the language here is cautious. Too cautious. Saying gravity affects time is like saying your hands affect the clay when you sculpt a vase. The real insight is this: gravity shapes the experience of time. And if it shapes time, that means it's not just moving through it. It may be co-creating it. Gravity without time. Let us run a thought experiment. Imagine a universe with no particles, no energy, nothing but empty geometry. There are no clocks, no sequence of events, no before or after. Is there still gravity? In classical physics, the answer would be no. But in modern quantum gravity models, the answer might be yes. Certain interpretations like loop quantum gravity or the Wheeler-DeWitt equation suggest that time is not fundamental. Instead, time emerges only when a gravitational field interacts with matter. In other words, time emerges from relationships, especially the relationships defined by gravity. Wherever gravity curves space, it also curves time, in effect creating a flow where none existed. Gravity sits. Relationship to entropy. Now introduce a new player, entropy, the tendency of systems to evolve from order to disorder. The second law of thermodynamics tells us that entropy always increases. This is the arrow of time. Eggs break. They don't unbreak. Stars burn out. They don't reignite. You age forward, not backward. But gravity and entropy are intertwined in strange ways. Consider a black hole. The most gravitationally extreme object in the universe also holds the highest entropy. Stephen Hawking discovered the surface area of a black hole, the event horizon, contains a precise measure of information loss. It has temperature, entropy, and therefore it's part of time's unfolding story. So maybe the deeper truth is this: time is born where gravity meets entropy. The expanding universe as a clock. Now zoom out. And here's the kicker. This acceleration is often attributed to a cosmological constant, a property of space-time itself. But what if that's just a clue that time itself is growing? As galaxies move apart, the geometry of the universe shifts, redefining distances, light paths, and gravitational gradients. Maybe what we're watching isn't just space stretching, but time unfolding. Cosmologists often describe this evolution in terms of a cosmic clock, not a physical object, but the changing state of the gravitational field itself. In this sense, gravity doesn't just need time. It tells time. And without it, the universe wouldn't tick. It would just be a timeless gravity. What if time isn't set real at all? That's the argument in some interpretations of quantum gravity, especially the so-called timeless ones. According to these views, the fundamental equations of the universe don't include time. Time is something we experience, not something that actually exists. It's a byproduct, a statistical artifact, a necessary illusion. In this framework, gravity is not acting through time, because there's no through. Gravity is simply the relationship between configurations. It's how the universe remembers what came before, even if it never really did. You move from moment to moment because gravity pulls the configurations into alignment. It doesn't need a clock. It is the clock. Philosophical implications. Let's breathe for a moment. This might seem abstract, but it cuts to the heart of our existence. Not just physically, existentially. Time feels linear to us. First this, then that. We are born, we grow, we die. But if time is emergent, constructed by gravitational relationships, then your entire life may be encoded in curves, in densities, in motion we can't yet decode. Maybe the past isn't gone, just folded into the field. Maybe the future isn't unwritten, just out of reach. And maybe you don't ride through time? A new definition of gravity. So let's end with a redefinition. Not gravity is the attraction between masses. That sets a textbook. Try this instead. Gravity is the shape of awareness as it unfolds. Or, gravity is the memory of the universe, etched into its fabric, carrying the rhythm of time itself. Because if gravity gives birth to time, then everything you've ever experienced, every breath, heartbeat, choice, is part of a gravitational song still echoing across the stars. Gravity pulls. Always. It doesn't push. It doesn't stunt, oscillate. It doesn't cancel itself out. Unlike every other fundamental force in the universe, gravity only works in one direction, toward the center, toward mass, toward collapse. Why doesn't gravity have an opposite? The other forces all do. To appreciate how strange gravity is, let's look at the company it keeps. The other three fundamental forces in physics. Electromagnetism has both attraction and repulsion. Positive and negative charges cancel each other out, creating balance. Strong nuclear force binds protons and neutrons in atomic nuclei. It's incredibly strong but short-ranged and is balanced by the nuclear repulsive force at certain distances. Weak nuclear force, responsible for radioactive decay, it's complex and asymmetrical, but it participates in interactions that allow particle transformations in both directions. Each of these forces has symmetry, opposition, opposition, a yin and yang. But gravity? It sets relentlessly one-sided. Gravity only attracts. There is no negative mass that repels regular matter, the way negative electric charges repel positives. Every bit of mass in the universe pulls every other bit of mass toward it. That's why galaxies form, stars collapse, black holes grow, and planets orbit. Gravity has no cancellation. You can shield yourself from light using a wall. You can block magnetism with the right materials. You can escape electric fields using insulation, but you can hide from gravity. Even if you're in the vacuum of space, 1,000,000,000,000 kilometers from the nearest star, gravity still reaches you, weakly, silently, inevitably. This imbalance has made scientists wonder, could there be anti-gravity? Attempts to discover anti-gravity have taken several forms. Negative mass, hypothetical particles with less than zero mass. They would theoretically repel normal matter, but we've never observed any. Repulsive gravity from dark energy. The accelerating expansion of the universe seems to be driven by something pushing space-time apart. This isn't traditional anti-gravity, but it acts like it. Modified gravity theories. Some models, like Mund modified Newtonian dynamics or scalar tensor theories, introduce corrections or counterbalances. Still, none have demonstrated a true opposite of gravitational attraction. Could anti-gravity be hidden in the vacuum? One intriguing candidate, the quantum vacuum. Empty space isn't actually empty. According to quantum field theory, it teems with virtual particles, pairs of particles and antiparticles that flash into existence and vanish again. Some researchers suggest that these fluctuations could create a pressure, a vacuum energy, that behaves repulsively. This is the foundation of the cosmological constant, a kind of anti-gravitational push that might explain why the universe is accelerating in its expansion. Still, it's not enough to counteract gravity on small scales. You can't use vacuum energy to levitate a rock or float your coffee mug. Its influence only becomes noticeable across billions of light years. So while it might be a kind of cosmic anti-gravity, it's not something we can feel in our daily lives. Not yet. Why gravity might not need an opposite? Here sits a deeper possibility. Gravity doesn't have an opposite because it doesn't need one. Consider this. What if gravity isn't a force in the traditional sense at all? Einstein didn't describe gravity as a force pulling objects together. He described it as the curvature of space-time. Mass bends space-time, and objects move along the curves. In this model, gravity isn't pulling anything, it's guiding it. Like a marble rolling down a funnel, the marble isn't being pulled, it's following a path. So, if gravity is just the shape of space-time, what would it even mean to have an opposite? You can't have negative curvature in the same way you can have a negative charge. You can have different kinds of curvature, warps that expand instead of contract, but they don't cancel each other, they just create different geometries. The role of mass and energy. Gravity arises from mass and energy. And here sits another strange twist. All energy contributes to gravity. Light has no mass, but it still bends space-time. So does pressure, so does tension. In general relativity, anything with energy density participates in shaping gravity. If gravity is the response of the universe to energy, then its unidirectional nature may be a reflection of a deeper truth. There's no such thing as negative energy in classical physics. And so, there's no inverse curve to generate a reversal. Everything adds to the warp. Some theories suggest that, while gravity doesn't have an opposite, the universe still finds ways to balance itself. For example, cosmic inflation. Right after the Big Bang, the universe expanded faster than the speed of light, a moment of brief anti-gravity-like expansion. Dark energy, a mysterious repulsive effect that might act like gravity's mirror image, though it doesn't cancel gravity, it just dominates it over very long distances. Holographic principle. Some models suggest gravity is an emergent property from deeper quantum information fields, meaning it only appears one-sided because of how we observe it from within. Metaphysical implications. Let's get poetic for a moment. If gravity has no opposite, what does that say about the universe? Maybe it reveals something about the nature of unity. Gravity brings together. It forms planets, stars, galaxies, and clusters. It weaves chaos into structure. Perhaps the absence of an opposing force is not a scientific mistake. In a universe of dualities, gravity is the reminder that some things only move in one direction, toward connection. It is the invitation to fall inward, to gather, to bond, to collapse into being. No push, only pull, only convergence. This might seem absurd. After all, gravity holds galaxies together. It pulls oceans into tides. It crushes matter into stars. It bends the path of light. And yet, drop a paperclip and a fridge magnet can defy the entire pull of Earth. Your hand can lift a rock with ease, while the combined gravitational force of 6 sextillion metric tons of planetary mass barely holds it down. Why is gravity so weak? And what if that weakness isn't a flaw, but the point? How weak is gravity, really? Let's talk numbers. Gravity is roughly 10 times weaker than the strong nuclear force. That's a 1 followed by 38 zeros. To put that into perspective, if gravity were as strong as the electromagnetic force, you wouldn't just fall when you tripped, your body would implode. Stars wouldn't shine, they would instantly collapse. Life, as we know it, couldn't exist. The laws of physics seem to require gravity to be weak. But why? Why should the force that holds the universe together be so cosmically polite? The hierarchy problem. In particle physics, this weakness is a major puzzle known as the hierarchy problem. It refers to the huge difference in strength between gravity and the other fundamental forces, especially compared to the electroweak force, which governs radioactive decay and electromagnetism. According to quantum field theory, these forces should be more balanced in scale, but they're not. Physicists have proposed many explanations. Extra dimensions. Gravity might spread out into dimensions we can't detect, diluting its apparent strength in our 3D space. String theory proposes gravity as a vibration of a different kind of string, fundamentally distinct from the other forces. Still, after decades of searching, no experimental evidence has confirmed any of these ideas. The hierarchy problem remains unsolved. But maybe it's not meant to be solved. Maybe gravity is weak for a reason. Imagine a universe where gravity was stronger. Just a little stronger. 10x, 100x, 1, 000x. And the balance between matter and energy would collapse. Stars would burn too quickly. Black holes would swallow galaxies. There would be no long, stable windows of time for life to evolve. In fact, some cosmologists argue that gravity's weakness is a fine-tuned parameter, a cosmic dial set precisely to allow stars, planets, chemistry, and consciousness. This idea connects to the anthropic principle. The notion that the universe must have the properties necessary to allow observers like us to exist. In this view, gravity isn't set weak by accident. It's supped weak so we can be here to wonder about it. A self-regulating universe? Another theory. Gravity's weakness is part of a self-regulating feedback loop. As mass clumps together under gravity, it generates heat, pressure, and fusion. But if gravity were stronger, stars would burn faster, explode sooner, and litter the cosmos with chaos. There'd be no time for complexity to emerge. Weak gravity allows for long-lasting stars that burn hydrogen slowly for billions of years, stable orbits that let planets stay in the habitable zone, galactic structures that done a stab immediately collapse into black holes. In other words, the universe restrains its own violence to nurture endurance, and maybe meaning. The hidden strength of gravity. But here sits the twist. Gravity set's weakness might be an illusion. While its effects are tiny on small scales, they accumulate across space and time. Unlike the other forces, gravity has no negative counterpart, so its influence never cancels out. Over large distances, gravity wins. It shapes the curvature of space itself. It controls the fate of galaxies. It governs cosmic expansion. So maybe gravity is weak locally, but dominant cosmically. It is the silent sculptor, the patient artist, the force that works not through speed or brute strength, but through persistence. Is weakness a form of intelligence? Let's zoom out even further. What if gravity's apparent weakness isn't a physical flaw, but a philosophical design? What if gravity is slow because life takes time? Gravity is soft because subtlety is more fertile than force. Gravity is weak because only the weak allow space for others. Consider this. The strongest forces in physics act only at tiny scales. Nuclear, subatomic, fleeting, but gravity reaches everywhere. Maybe its whisper is more powerful than a scream. Simulated universes and design questions. If our universe is simulated, as some theorists suggest, then gravity's weakness could be an engineering choice. In digital simulations, high-precision calculations cost energy. Gravity, with its smooth, large-scale gradients, is easier to simulate than chaotic electromagnetic fields. From a simulation standpoint, a weak gravity field is computationally efficient and aesthetically pleasing. Could the architects have chosen this constraint deliberately? A universe of gentle pulls, of time stretched wide, of meaning slowly assembled over billions of years. Gravity sits weakness as a spiritual metaphor. In the end, whether designed or emergent, simulated or real, gravity's gentleness carries a strange poetry. It reminds us that the smallest forces can have the largest effects. That quiet is louder than noise. That what binds us is not what dominates, but what lingers. Every time you drop a pebble, gravity responds. Every time you fall, it catches you. Every time a planet spins, it's dancing to gravity's music. And all of it, the stars, the dust, your own body, fragile, and yet unbreakable. Gravity is everywhere, but what is it really? We measured its pull. We mapped its effects. We've even watched it ripple through space-time in the form of gravitational waves. And yet, the true shape of gravity remains elusive. Is it a field like magnetism? A flow like water bending around rocks? A fold in the invisible fabric of reality? Let's travel through three interpretations: field, flow, and fold, and explore how each reshapes not only our understanding of physics, but of reality itself. For centuries, gravity was seen as an invisible force, one mass pulling on another across empty space. Then came Newton's equations, which described this force with uncanny precision, but they didn't explain how gravity worked, only that it worked. It was Einstein, in 1915, who changed everything. According to general relativity, gravity isn't a force at all. It's the result of mass warping space-time. Objects don't pull on each other. Instead, they curve the stage they sit on. Imagine placing a bowling ball on a rubber sheet. Smaller objects roll toward it, not because they're attracted, but because the surface itself is bent. This curvature, or distortion, is what we now call the gravitational field. So in this view, gravity isn't transmitted through space. It is space, bending and flexing around mass and energy. It sets a poetic idea that matter tells space how to curve, and space tells matter how to move. But it raises an even deeper question. Is space made of something? If gravity is a field, then what is the field made of? We know that electromagnetic fields consist of virtual photons. Quantum fields, like those of the Higgs or the electron, have particles. So, does the gravitational field have particles too? Enter the graviton, a hypothetical massless quantum particle that would carry the force of gravity, similar to how photons carry light. But here sits the catch. No one has ever detected a graviton, and many physicists believe we never will. Why? Because gravity is so weak, and gravitons would interact so faintly with matter, they might be effectively undetectable with any conceivable technology, if they exist at all. So perhaps gravity isn't a field made of particles. Perhaps it's something deeper. Gravity is a flow. Let's step out of physics for a moment, and into metaphor. What if gravity is more like a current, a flow of reality from one configuration to another? Think of rivers. They don't pull the water, they simply shape the path, and water follows. Similarly, gravity might be the result of a flow in the underlying geometry of the universe, like energy taking the path of least resistance. There are theories that suggest gravity might be emergent, not fundamental but arising from more basic interactions like temperature or pressure. One such idea is the entropic gravity hypothesis, proposed by physicist Eric Valindi. According to this theory, gravity is not a force, but a consequence of statistical probabilities. Space itself has information, and gravity emerges when that information reorganizes. In other words, gravity might be the result of the universe constantly flowing toward disorder, and matter just gets caught in the current. Gravity is a fold. Now let's go even deeper. What if gravity is neither a field nor a flow, but a fold, a wrinkle in the shape of reality? String theory and its cousin M theory propose that the universe has more than 3 spatial dimensions, perhaps 10, perhaps 11, maybe more. In these frameworks, what we experience as gravity might be the shadow of higher dimensional activity. Picture a 2D being on a sheet of paper. If you fold the paper, that being might suddenly find itself next to something that was once far away, without ever moving in its own world. To that being, it would seem like some unseen force had pulled the distant object close. But in truth, it was the space itself that folded. It would mean that mass isn't set pulling on space, and gravity is simply how that bend feels from our limited vantage point. Experimental clues. Well, we've detected gravitational waves, literal ripples in space-time created by massive events like colliding black holes. These waves travel at the speed of light, and their detection by LIGO in 2015 confirmed one of Einstein's final predictions. On the other hand, we've never observed gravity to act discontinuously. It flows smoothly, like a field, and yet, at the edges of black holes, things break down. Time slows, space stretches, equations diverge, and so physicists suspect that gravity's true nature can only be revealed by quantum gravity, a theory that successfully merges general relativity with quantum mechanics. We're feeling the shape of something with eyes closed. Why it matters? Does it really matter if gravity is a field, a flow, or a fold? Yes, tremendously. If gravity is a field, then space is a physical object, and we can warp it. If gravity is a flow, then we are part of a thermodynamic dance, and time may be more fundamental than space. If gravity is a fold, then we live in a multiverse, and dimensions beyond our own shape our fate. The shape of gravity is the shape of everything, of how the universe expands, of why time has a direction, of what might lie beyond the horizon of a black hole, of how consciousness might be embedded in geometry. To know gravity is to know the architecture of existence, and we're still just scratching the surface. For centuries, gravity has been framed as the backdrop, the silent force pulling matter together, shaping stars and keeping feet on the ground. It's impersonal, predictable, and beautifully indifferent. But what if it isn't just the invisible stage upon which the universe acts? What if gravity is participating? What if, in ways we don't yet understand, gravity isn't merely responsible for cosmic structure, but is also a crucial ingredient in that most elusive phenomenon of all, consciousness? The consciousness question. Let's begin with the riddle. Why does the brain, a 1.4 kilogram blob of wet tissue, generate an inner world? A subjective self? A feeling of being? We've mapped the neurons. We understand action potentials, neurotransmitters, even decision-making circuits. But no amount of biological wiring has explained why those circuits produce awareness. It's the infamous hard problem of consciousness. The gap between objective processes and subjective experience. And that sits where gravity walks in, silently, mysteriously, maybe even crucially. Or, where quantum physics meets the brain. Here sits the gist. Consciousness isn't set just computation. Penrose argues that the human mind transcends the capabilities of classical algorithms, that something more is going on. The more might be quantum. Hemmerhoff suggests that microtubules, structural components inside neurons, could sustain quantum states, potentially influencing cognition at a quantum level, and gravity might collapse those quantum states. Penrose introduces a radical idea. Gravity could be the force that collapses quantum superpositions. Not observation, not measurement, but gravity. If correct, this would mean gravity doesn't just shake planets. It also decides when a quantum possibility becomes a singular experience. And if that process occurs in the brain, is gravity the link between matter and mind? Consider this. Gravity is the only force that acts on everything with mass. It shapes both the largest structures, galaxies, and influences the tiniest scales, quantum fields, potentially. It connects indiscriminately, endlessly. So what if consciousness emerges not from isolation of brain parts, but from their connectedness, from their integration into a coherent whole? In this sense, gravity could be the glue of cognition, ensuring every part of the brain shares a common informational field, a unifying framework, a singularity of perception, not by broadcasting signals, but by curving the very field in which they arise. This isn't set mainstream neuroscience. Not yet. But it's not purely fiction either. Some theories now suggest that spacetime itself may be emergent from entangled information, that gravity is what information feels like when it's woven together across a system. If true, gravity might not just pull on your body, it might bind yourself. Even if you set aside quantum theories, gravity has a subtle but real influence on brain operation. Astronauts in microgravity environments report disrupted spatial orientation, altered emotional regulation, shifts in cognitive performance. On Earth, changes in gravity, from standing to lying down, cause shifts in blood flow, pressure, and neurochemical distribution. Over time, gravity may shape the evolution of consciousness itself. After all, our ancestors didn't evolve in zero-G. They evolved under the steady pull of Earth. Every structure of the body, spine, inner ear, even the fluid dynamics of the brain, was sculpted in gravity's presence. Could it be that awareness, too, is a response to that pull? That consciousness is a dance choreographed by the way gravity curves our inner and outer world? Black holes and the self. Let sex venture into deeper space. Black holes, those dense, mysterious points in space-time, are often thought of as cosmic endpoints. But some physicists suggest they might also be information engines, that what falls in is not destroyed, but encoded on the event horizon. This raises an eerie parallel. Your consciousness isn't the neurons firing in your brain, it's the pattern of information those neurons sustain. Could your mind, too, be a kind of informational hologram, encoded not in flesh, but in the curvature of your personal space-time? Is gravity the hard drive, and consciousness the running software? Is your selfhood less a fire, and more a shadow of geometry? Reframing the illusion. Let's return to the idea from earlier in this series that gravity might be an illusion, a byproduct of deeper information processes, an emergent effect of entropy balancing out. If that's true, then gravity isn't a cause. it's a consequence. And if consciousness emerges because of gravity, then consciousness too is not a cause. It's such a consequence of consequence. A second-order echo of how information seeks balance, how the universe unfolds. And if so, then you are what happens when the universe needs a way to observe itself, and it folds inward through the force we call gravity. You are the curvature of the observation, the final trick. So here we are. We asked, what if gravity is just an illusion? But the deeper question is, what if it's the only real thing and everything else, space, time, mass, thought, is built upon its lie? What if your experience of selfhood is simply what happens when gravity curves not just space, but attention? In the end, gravity's greatest trick may not be pulling apples from trees or stars into spirals. Its greatest trick may be bending information into identity, into you. You've drifted through illusions now, felt the tug of a force that might not exist, and the weight of truths that may never be proven. You've wondered whether gravity is the fabric beneath your feet, or just a narrative your neurons have learned to trust. You've followed the spiral of falling apples and orbiting galaxies only to arrive at the edge of something stranger, the possibility that everything you thought was fundamental might be emergent. And now, you're still here, floating, listening, questioning. Let's not rush away just yet. Let's sit at the edge of the universe together and breathe. A force that may be fiction. We began this journey by asking a question that sounds absurd to the uninitiated. What if gravity is just an illusion? But as we pulled back the cosmic curtain, we found a surprising crowd of physicists, philosophers, and dreamers standing right there with us. Gravity, once so comfortably explained by Newton's apple and Einstein's geometry, now flickers under quantum scrutiny. Some say it's not a fundamental force at all, but an emergent property of thermodynamic laws. Others believe it arises from information entanglement across invisible boundaries. But if gravity is a story, it is a powerful one, because it tells us where we belong. It whispers that there is a center, even when there isn't, that there is a direction, even in an expanding void. Consider this. Everything you've ever experienced has occurred under gravity's influence. Your brain evolved under it. Your breath rises against it. Even your dreams are framed by it. Because REM sleep depends on blood flow, and blood flow depends on gravity's press against your body. Without gravity, there is no up, no down, no falling into a lover's arms or lying on grass under stars. Without it, even metaphor fails. We fall in love. We rise to the occasion. We feel the weight of sorrow. We are pulled toward truth. Gravity is baked into our language, and deeper still into our meaning. So if gravity is an illusion, it is one that defines our sense of what is real. And that, paradoxically, makes it real in a different way. Not physically, but phenomenologically. Not as a fact, but as a felt presence. Like time. Like selfhood, a mirror of mind. Let sits lean in deeper. In many theories of consciousness, unity is key. The brain is not simply a collection of signals, it is a network that binds them into a single narrative, a seamless whole. Gravity, too, does this. It unifies. It does not discriminate. It gathers. It collapses. It says you are part of this. And maybe, just maybe, this is not a coincidence. Both operate through unseen influence. Both require curvature, of space, of thought, of self. And both leave us wondering what is real and what is simply our way of describing the incomprehensible, the final illusion. If you've come this far, you're already comfortable with doubt. You've entertained the idea that mass might not exist as you think. That acceleration might be perception. That space might be stitched from information. That your body is floating on a planet that's not really pulling you down, just guiding you along a curve. So here is one more illusion to consider. That there is ever an end. We crave conclusions. They let us close the book, shut our eyes, say I understand, but the universe doesn't end in paragraphs. It loops, it folds, it revises itself. Maybe gravity isn't set a force. Maybe it's a metaphor for closure, the feeling of being pulled toward resolution. And maybe consciousness is what happens when that resolution never quite arrives. One more thought before you drift. There is no final truth in physics, only models that get more accurate. Each answer is a door. Each door opens into another field, another theory, another paradox. It may be the ultimate placeholder, the symbol we assign to the way things appear to hold together, even when they're flying apart. You are still here, and that perhaps is the only real force in the cosmos. The capacity to wonder, to stay awake inside the illusion, to feel the pull of questions not yet answered. So go ahead, fall asleep now, if you must, but know this, you do not fall into sleep. You fall with it. And somewhere in the curves of space-time and synapse, that motion, that softness, that surrender, might be gravity set's final illusion, or its most honest truth. Good night, traveler. USEP already begun orbiting the next question.